1 and a dimension here. That's A. That's going to be okay. These are going to be in meters. So this would be B. Now after that, first I'm going to find the cutoff frequency for the 1 mode. And by the way, what would that be? That would be C, right? Over 2A, correct? So that would be 3 times 10 to the 8th meters per second divided by 2. And A is this dimension right here. So it's really what? That's 1 times 10 to the minus 2. It's 2 times 10 to the minus 2, right? And that means it's really 1.5 times 10 right here to the 10th, right? Or it's 15 gigahertz. Do you all agree with that? All right. So that's the 1 mode. Now I'm going to say this is the waveguide, dimensions, cross-sectional dimensions. I'm going to say the length of the guide here. Here's my waveguide. Length of the guide is going to be 2 meters. And I'm not going to have any source impedance at all. So I'm just going to go ahead and feed this waveguide, you might say, with a voltage source of 100 volts at 0 degrees. All right. And the frequency I'm going to feed it at is going to be 20 gigahertz. You can ground this too, right here, the outer part. And I'm going to have a load over here. I'm just going to show it this way. I'm going to have a load. And ZL is going to be 100 ohms. Now, this is a kind of a quiz problem I would give you on Friday. How's that for saying that out loud? Everybody got that? This is the kind of a quiz problem I'd give you on Friday. And I draw it up better, but I got the length of the guide, I've got the voltage source, I've got this, and I got ZL is 0, right? So let's go through it. First, I need to figure out what the cutoff frequency, well, I did for the 1 mode. So I got the cutoff frequency FC10 would be 15 gigahertz. Somebody want to tell me what FC20 is? Anyone?
Would it be 30 gigahertz?
Absolutely twice that, right? If I meet the requirement, is the dimension, vertical dimension, or I should say, if I take the vertical dimension by 2, is A greater than it? Absolutely, right? So it meets the requirement. So that's the 2 mode. I'm at 20 gigahertz, therefore I'm between the first and the second, only one mode of propagate. You all agree with that? So only one mode. Give me 1 second. My bad. So only one mode will propagate. And if only one mode propagates, now listen, the next thing I need to do is find out what the actual value of K is. Remember, K is equal to the square root of 1 minus FC over F squared, right? We're going to use this a lot. Are you with me, guys? All right, so what's that going to be? Well, K would be equal to the square root of 1 minus, now think about it. FC is 15 gigahertz, right? I'm propagating at 20 gigahertz, right? So it's going to be 15 over 20 squared, or it's square root of 1 minus, and that would be what? 3/4 squared, or it'd be 9/16, right? Square root of, y'all with me on this? I'm just putting the numbers down so you understand. So that would be K. Now, once I have that, right? Then I know beta in the guide here, right, is beta unguided times K. Let me see if I can show you that in the book, because I'm throwing a lot of equations out. And I want to make sure I'm not seeing what I want. I'm sure Wentworth does this. He's got the equation for beta in the guide, but he doesn't simplify it. I'll just leave it like this. I don't see the equation I'm looking for. Anyway, beta unguided is just equal to omega times square root of mu epsilon. Okay, and we'll assume our guide is air filled. So if that's the case, then this is really equal to omega divided by C would be beta unguided. Do you agree with that, everyone? And therefore, this would be beta guided would just be equal to K times omega over C. I'm going to do this in a minute, but I want to get all the things down. So now I have that. And now my first step is to get the input impedance. Actually, you know what? I made ZS 0, so the actual voltage is V prime. So because I made ZS equal to 0, V prime is equal to the source voltage, and that's 100 volts. And I'll put it down. Don't worry about the phase. Are you with me on this, class? I'm going to let you catch up and turn the page. Okay. Everybody good? I'm going to turn. So now we think about what's going on. I got this waveguide, and I got a load here. This is the length, right? I think I made the length 2 meters, correct? Now, here's what I need. I know it's in the 1 ohm mode. I know this is the source voltage. It's 100. I know the frequency is 20 gigahertz. I know the cutoff frequency is 15 gigahertz. All right, so the next thing I need is the impedance of the TE 1 ohm mode. That's going to be the characteristic impedance of the guide. And ZTE 10 will be equal to really the characteristic impedance of the waveguide, with the material inside the guide, unbounded, divided by K, right? And that's really 120 pi. It's just the free space because it's filled with air over K. Now I have that. I'm going to do all this. You with me? After I do that, the next thing I need to do is find the value of V0 prime. And I know V prime, or V0 really, V prime is just equal to Vs. It is the voltage just on the inside. And that means this value here is going to be V naught plus times E, and it's going to be to the J beta guide times L plus E to the, plus really gamma, the reflection coefficient, my bad, times E to the minus J beta guide times L. Now what I need to do is find V prime, V0 plus, pardon me. And that's going to be V prime over this mess. I want to make mention of one thing. Lots of mistakes made with your calculators in this calculation, typically. Just giving you a heads up. You might want to star that warning. You're going to make a lot. So do this several times. Make sure you got your calculators down. You know what's going on. These are radian measurements, remember. Okay, now I have that. And I need V0 prime. Here, I don't really need the characteristic impedance yet, but I mean the input impedance yet. I got to get that, and I need to get gamma L, right? I've got beta guide is equal to just, that's equal to beta unguided times K. And I need the reflection coefficient. Reflection coefficient is just ZL divided by, or I should say ZL minus Z naught TE 10 over ZL plus Z naught TE 10. All right. I'm trying to put the steps down again. I know you guys have been with me hanging in there, and I appreciate it. Now, for everybody's hanging in there, thank you. I got that. I'll be able to get it correct, class. Once I get this, I can get this. I need this first to get that. I know what V prime is. Once I have this, I know the voltage at the load is just going to be that V0 plus times 1 plus reflection coefficient at the load, right? And at that point, we could get the current. I made it a purely real load, 100, didn't I, class? So if it's 100 ohms, the current and voltage are in phase. And if you want the power at the load, since this is just a 100 ohm load, we could say the power at the load is just going to be 1/2 magnitude of voltage at the load squared divided by ZL magnitude, because ZL is real, strict real. Okay. Let me go through this and show you how the numbers work, okay? Take a deep breath if you want, relax. So, and I'll take pictures of all this and put it up there for you. I don't know if it's going to help you or not, but I'll do it for you. So, tell me when you guys are good for me to move on. Nathaniel, are you on campus?
Yes, sir.
Is
Yeah.
the parking bad, or is it okay? In other words, is there a lot of cars everywhere?
Yeah, there are a lot of students around here.
Sorry to hear that. Well, no, I'm not. Students aren't supposed to park on campus until 5 o'clock, right? Unless you have a special permit. But if they're doing it, so be it. Now here I'm going to do this thing, and I like MathCAD myself. I don't have the full version operational, but I'd encourage you guys to get this because it's so easy to use. So I'm going to go down here, start. And let's see, I always do this with MathCAD. It doesn't have a built-in pi thing, so I have to go up here and just make that equal to pi. And then after that, I'm going to start by saying a to naught right there is equal to 120 times pi. What else do I need? My source voltage is 100 volts, right? Now, after that, I know that K for my thing, well, let me do this. I know F, operational frequency, is 20 gigahertz, right? And then now I'm trying to show you this stuff, and I'll take a picture of this too. Now I want the cutoff frequency for the 1 mode. So FC1, comma O for this one is going to be equal to sorry. Let me do it this way. I'm just going to call it FC. That's equal to C over 2 times A, right? And in my case, A, what did I make A? Was it 0.01?
It was
.01.
1 centimeter.
0. All right, and it has C in here, but as a, it'll put units everywhere, and I don't want to mess with that. So then I get down there. Now the next thing I'm going to do is find K. You can check me on this if you get a different value, okay, guys? And that means when I take a look at this, I got A to naught there. The impedance, I'll just call it ZTE, is equal to A to naught divided by K, because it's a TE10 mode, right? Everybody? That's the impedance, the feed impedance that little antenna feels when it feeds it. So now I got everything. Now I need to go ahead and now I got to go ahead. Let's see what else. I got. I need to get the reflection coefficient at the load, right? I'll just call it gamma. I'll just call it gamma. How about gamma? I'm using this for the reflection coefficient. Well, that's going to be Z load, right? Minus ZTE over Z load plus ZTE. And Z load, I think it was 100 ohms, wasn't it, guys?
Yeah.
Oops. So let's see what I get here. This should be strict real. With me? Now I have ZL. After that, remember my V prime, I'll call it V plus, just VP for now. That's equal to I better show you this. It's equal to V source because that in fact was the voltage just on the inside. It's that, right? And then it's going to be divided by, now follow me in this, I got to get beta guide in a second. Here it's going to be E to the, hold it. I'm going to call this capital F, and I'm going to define it up here. And I'm going to say that F equals EXP to the J times beta guide times L plus gamma L times EXP to the J times beta guide times L, but there's a negative sign here. And I got two things. I got to take this above or else it won't work. Oh yeah. Remember what beta guide was? Well, how about beta unguided? Do you remember what that was? It was
Omega over
omega.
C.
Yeah, omega over C. I didn't put omega in here, did I? No, so I got to put, I'm using a W though, is just 2 times pi times F, right? And then I can say that beta guide is equal to beta unguided, right? And it's going to be that times K. Right? Well, I just mentioned something. The wavelength in the guide, I'll call it lambda in the guide. That itself, I'll just call it lambda. Lambda G. That's equal to 2 pi over beta in the guide. And I want to make mention of something else too. Now, that's beta in the guide, right? Right there. The free space lambda would just be C over F, right? Right? But if you take free space lambda right here, and you simply divide it by K, then you get lambda in the guide. That's something to remember too. I know I'm throwing a lot at you, but I'm just showing you different things that are useful. So now, I didn't put L down, did I? So I'm going to put L. I think the length was 2 meters, wasn't it? Can you confirm that? So now I got this, and here, the reason I wanted that F was because I want the actual value. This is V plus, and I can't put a plus here. So what is V plus? This will be complex, I think. All right, so that's the voltage V plus. You with me? Now, how much voltage goes to the load? This is the voltage at the load. Well, that's V plus, right? Do you remember what I do now? I multiply it by, anyone?
1 plus the reflection coefficient.
1 plus the reflection coefficient, right? And that's what I get. You'll notice that's complex. Everybody? That doesn't matter. You care only about the magnitude. Now, my load is strictly real, correct? Now, the power delivered to the load, I'll call PL, that will be equal to 1/2 times, and then it's absolute value. It's MathCAD's nice. I can hit that and it's absolute value of V load squared. And then it's just divided by, because it's strict real, this is the reason I don't have to do V times I conjugate. Now I can just divide this whole thing by Z load. And that's the power in watts. And that's really the way it works with waveguides. Now, there's something I didn't tell you. You know, whenever you feed a waveguide, in order to get perfect coupling from the source that I assumed, you have to impedance match it. And even then you don't get perfect coupling, do you? You still, the most you can get if you impedance match something is half the actual power, right? Or half the voltage if you impedance match something. Do you all remember that? The maximum power possible, and this is true with waveguides, there is no such thing as having a source without a characteristic impedance. I omitted it because I'm just saying this what do I call it? This VS here, I assumed was the voltage on the inside. But because it's really, you have to use voltage division between the feed impedance and the actual source impedance, your input impedance and the source impedance. You'll see that as your waveguide impedance and your source impedance start getting further and further different, you'll start getting a huge amount of power reflected. Did I tell this class a story about the time I had a solder bowl on the antenna or not? Okay, well, I've got real personal experience with this, and it was money. So you don't forget when you lose a lot of money, possibly lose a lot of money. Thankfully, I did. So I designed an antenna array, and it was for a synthetic aperture radar. How would we do that? It's a good question.
Would you impedance match your waveguide to your load?
How would you
And
do
then
that? If we can vary the
Uh,
load impedance, what would you do? Not the waveguide impedance.
if you
That's-
could vary the load impedance, you said?
What's the one thing you're looking at? Isn't it this right here? You want to make
Yeah.
the reflection coefficient 0, don't you? So if the load impedance is the ZETE impedance at that frequency, then you got a reflection coefficient of 0. Then all the transmitted power is dissipated, none's reflected. That's the idea. Another thing you've got to remember, especially when you're dealing with high power things like antennas that you're feeding that are radar antennas or something, you never want any significant reflection coefficient because that power comes back at you. It can blow up a power amplifier or something. Remember that. And one other thing, do you know what makes a waveguide? Well, let me do it this way. What makes something that's a coax cable act like a coaxial cable with a characteristic impedance versus just two pieces of conductor tied to something? There's one real important thing. Go ahead.
Is it that their magnetic fields cancel each?
Now, here's the thing. If you have a coax cable, the length of the coax has to be at least 1/10 of a wavelength for it to start behaving as a coax cable, where the characteristic impedance is important. If it's shorter than that, it looks like two pieces of wires. That's the rule of thumb. So it's got to be at least 1/10 of a wavelength long in order to start talking about it acting like a wavelength and having its own characteristic impedance. Otherwise, it's not an abrupt change, but that's the rule of thumb. Now, when you're getting into things that are like 1/3 or half or 2.5 wavelengths long, then that looks like an actual transmission line. For a waveguide, this is important. The wavelength in the guide, not free space, the wavelength in the guide right there has to be, or the thing has to be at least 1/10 of the wavelength in the guide, which is different than the free space wavelength. Do y'all follow me on that? Because think about this. What's the wavelength in the guide? It's that. What's free space wavelength? So what's the ratio of the two? Oops. It's actually K, or 1/K, pardon me. Wait a second.
You need to make round on the base.
Huh?
You round on the bottom needs to be lowercase l.
Yeah. So if you take free space wavelength and multiply it by 1.512, the actual lambda in the guide. And as this frequency of operation starts getting closer and closer, or lower and lower, let's put it around 15.03. You're just barely over the frequency, cutoff frequency. Watch what happens. See how that wavelength starts getting longer and longer and longer, and all this stuff. Now your power goes way down too, doesn't it? Look at the reflection coefficient. Now it's almost 1, right? Just about everything's reflected. That's real important to see. With me, guys? Okay. This is an office hour, so I'm allowed to do this. So any other questions or any questions? I'm long-winded today, I'm sorry. William, you okay with this? And you recorded it, right? So
I recorded it on the cloud, and then when we went to the office hour, I recorded it on my computer. But I don't know, the cloud recording is kind of giving me trouble though, but I'm looking into it.
I bet you if you go on Google and look, you'll find, or YouTube, you'll find methods to take that cloud and upload it to YouTube, because kids do this stuff left and right now. They know they're going to disappear on Zoom. Something I'm going to say, the quiz on Friday, God willing, that will be there, will be on waveguides and waveguide-like problems like this. So I'll give you a few. You all see how this parallels exactly what you did with transmission lines. The only change is the length, I should say beta in the guide, right? That's the one thing. And the characteristic impedance changes with frequency in the TE10 mode. Got it? Any questions? And I appreciate you guys turning your cameras on. I know, I mean, do you have any other questions? By the way, this is the free version of MathCAD. If you get the paid version, you get some more version. I love